Hello, guys. How are you guys doing?
Good. How are you, Dr. Jones?
I am doing pretty good. Um, Other than toddlers running around, got my house all crazy, but pretty good, pretty good, pretty good. How about you guys? How was the test? Was it okay? How did y'all feel about it? Yay, nay. Um, did anybody have questions about the lab practicum? Because I got some. I didn't know what classes it came from, but I got an email from one of the higher ups that was asking about the lab practicums, and they weren't sure how the lab practicums was going to go. So I just wanted to get feedback from everybody as far as that. Did y'all understand that? Y'all knew what y'all needed to do? I just need to put up the rubrics for that. I know somebody was concerned about it, and I wasn't sure who it was, but I think that's one of the things that I think our department um, that came back on the survey, they was concerned about lab practicums. Um, as far as what you guys are going to do. Um, Technically, what I am just planning is that you just write the paper and you do a voiceover PowerPoint. So in PowerPoint, and I'll pull up PowerPoint real quick. Hold on, let me share my screen and I can show you guys while I'm on here. I'm gonna slam my video off and then let me pull up the PowerPoint. Give me just a second. Let me set it up. And um, share screen. All right. So in PowerPoint, what you can do is you see that I got up different things. You can set up the slideshow, and I'm gonna just make it a little bit bigger. Um, let's see, insert. Trying to see. Um, you can. It actually got Zoom in there if you want to do it that way and record it, but there is a way. Um, you can record it right here, and what you can do is record the slideshow, and when you record it, you can record everything on each slide, what you want to say about that slide. It does not matter, but you can record what you want to say about that slide, and then when you save it, and I'm gonna just do it right here, you can hit save as. And then if I wanted to save it, you can actually save it as a MP4 video. And you can save it, so you can record it. I don't have to see you. If you want to put your little picture at the corner of it, it's fine. You don't have to. But you can save it as a MP4 video, MP4. And then you can just I'll do with that is associated with my um, what is that called? My YouTube channel. I have a Gmail account. I have several of them. You can upload the videos to. I'll make my Google Drive shareable, and that's mostly just my videos there. And you can upload it to that, and that's what I'll do, or make a Dropbox so you guys can upload it. That is all that I'm going to want you to do. That's pretty much it. That'll take the place of you actually standing up, giving the video. And I was planning on doing that anyway, just having you guys do a voiceover PowerPoint, because I know you guys got other classes and all of that stuff, but it will be just like y'all did last semester. Um, no more than 10 minutes. It doesn't have to be that long because I don't want the videos to take up a lot of space. But you can do it via that and just save it, and it'll be easy to do, and that'll be a lot easier. So I'll put all of that together today and put up the rubrics for that this week. So that's all what you're gonna really do is just a paper on whichever layout, and just do your paper in your presentation. That's pretty much it, and that'll kind of make up for, instead of you guys having to write the paper and then present it in class. That's just the same. So, any questions about that? Everybody saw what I did as far as that. Um, like I said, it just basically, you can record the slideshow. And I mean, you can stop at each one. And the really good thing about this, because I've done this for some of my other classes, is that each one, you can record something to that particular slide. You can stop it, you can erase it, you can pause it, and you can put it together and save it as an MP4. So it's really cool. And like I said, you can do that right in PowerPoint. So you don't have to really worry about any of that. So if you want to, if that's the easiest way, I can see to do that as far as doing the presentation itself. And like I said, I'm going to probably be doing that anyway moving forward, just so it doesn't take up presenting during class time, and people can actually do it on their own time. All right. Chapter 17 is what we're going to get started on. We're going to do 17, 18, and probably jump to chapter 23 for this test. I had some topics here. And then we're going to talk about, there's some other chapters that we are going to do. We are going to do 19, 20, and 21. I am going to go ahead and pre-record those. And the reason why I am going over those is because Dr. Craig sent me a list of topics that are going to be covered or should be covered on your guys' final exam. I have to make the exam look like the standardized exam, and there are certain topics that have to be on the exam. And so those particular chapters have to be on there because those topics are on the exam. So I'm gonna have to cover that with you guys. I didn't want to, but because it has to be on the exam, that's what I have to do. So what I will do is I would give you a broad list of topics that's going to be covered, but your ACS study guide book, if you got it, in general, don't worry, yours is coming, because I was checking on a few extra things and seeing if some of those topics were covered in the book, and he just got them to me. That you need to look in your book to make sure that you study those particular questions and everything. But that's what I have to do. And so I just want to make sure that all of the topics are covered for the exam. And so for you guys final, I will direct you toward what you need to focus on and study and everything like that. But some of those topics have to be covered, and he wanted those covered for the exam. And so he gave me those topics, and a lot of it we already have covered, but those chapters have some additional topics in there that we do need to go over. So I just wanted to make sure that I covered that with you guys. Okay, so let's get into chapter 17. And chapter 17 is really giving you an overview of pretty much what to come. So Chapter 17 is going to talk about your carbonyl groups. It's going to talk about aldehydes, ketones. And chapter 17 is really the overview of everything else that is coming. The last 3 to 4 chapters of the book, we're going to get into when it comes to, for those of you that are going to be taking biochem next semester, and for those of the ones that are taking biochem this semester, they are getting some of those questions directly from this book. So because some of the stuff, it does overlap with organic and biochem, and there's an overlap there. So the chapters that we don't get to in this book now, definitely you're going to have this stuff in the next book. So what I'm going to do is upload, I think I uploaded all of the slides. Make sure you keep those slides, especially from chapters 25 on to 29. Well, I'll say 24 to 29. Keep those chapter PowerPoints, because I will cover those when we get into biochem, because I'm going to sub those in with some of the stuff that we're doing now in biochem, and I see the overlap. So make sure you keep those, because I'm going to discuss those as well in biochem. So just to make sure, but we're going to cover up to chapters 24. So we're going to try to finish up the last few chapters. Like I said, those chapters are very important because those have to be on your exam. Okay, carbonyl groups. There are 2 classes of carbonyl groups, and I think this is the part of organic chemistry that I really started to really enjoy when it comes to carbonyls groups. So these are compounds that have only carbon and hydrogen bonded to the carbonyl. So we're dealing with aldehydes and ketones. And the other thing is these compounds contain an electronegative atom bonded to the carbonyl. And so there's some different ones. You can have carboxylic acid, acid chloride, you can have an ester, or you can have an amide. Now, with that, you can have electrostatic potential map of the carbonyl group. Now, what this map shows you is the electron deficit carbon and the electron rich oxygen in the carbonyl group. So the carbonyls are very important, and they play a role in a lot of different chemistries. And so the carbonyl group is very important. Now, what about the group structure? Now, with this, you have to pay attention to the different types of reactions and what they really undergo. Now, when it comes to carbonyl groups, they are sp2 hybridized. They are trigonal planar, and they have bond angles that is around approximately 120 degrees. In these ways, the carbonyl groups resemble the trigonal planar hybridized carbons of a carbon-carbon double bond. That's mostly the way that they look. Now, the difference is carbon-oxygen double bond, carbon-carbon double bond. The difference in those two is the electronegativity is really different. So that oxygen is electronegative. That means that bond can be polarized, making the carbon electron deficient. So if you want to look at it, you can look at it from the way of a resonance description, and that's what they do here. So they look at what is the major contributor to the hybrid. It can go to a minor contributor to the hybrid, and then you can see where it's polarized at. Now, when it comes to carbonyls, they are electrophilic and they react with the nucleophiles. So you see there, you see your pi bond, you see your electrophilic carbon, and that's what it is. That's the general reactions. They electrophilic, they react with the nucleophiles. Now, aldehydes and ketones, how are they made? Those are usually formed from addition products, and that is a two-step process. And with that being a two-step process, it's a nucleophilic attack followed by protonation, meaning that you're going to have a hydrogen coming off somewhere. That's what's going to happen. You're going to have that hydrogen proton coming out somewhere. Now, what you see here is the mechanism. So the nucleophile attacks the electrophilic carbonyl. That pi bond is going to be broken, and then you're going to move that electron out on the oxygen, and you're going to form, instead of sp2, you now have sp3. That's what's going to happen. And then your protonation going to happen. You're going to have negative charge oxygen by water, and it forms as an addition product. So that's what actually happens. Now, what about a reactivity? You got all this going on. Now, you got your pi bond that is being broken, and then you got two sigma bonds that are formed. So you got your elements that are added across the pi bond. Aldehydes are more reactive than ketones. Let me say that again. Aldehydes are more reactive than ketones toward the nucleophilic attack for both steric and electronic reasons. What happens is, because of the aldehyde, it's less crowded, it's less stable, and because it's less stable and less crowded, it's going to be more reactive. Now, the ketone is a little bit more reactive because it's not as much there, and so it's stable. So usually when you form ketones, you form a more stable compound than the aldehydes. And so that's what happens. Now, when you have these carbonyl compounds with leaving groups, they can react with those nucleophiles, and they can form different types of substitution products, and they're still going through a two-step process. Now, you got your nucleophilic attack and then your leaving group. Now, in this case, you got Nu replaces Z, and then a nucleophilic substitution reaction. Now, this is called nucleophilic acyl substitution. This is what happens. And so you see that process right there. Now, what about this? Now, you can have groups. Now, you can have different types of Z groups, but it just depends. If your Z group is better leaving group, you can have a more reactive RCOZ in the nucleophilic acyl substitution. So what happens is you can have something that is less reactive, and then it becomes more reactive. Now, which ones? You got your acid chlorides, which have the best leaving group because of that chlorine. They are the most reactive carboxylic acid derivatives, and the amides will have the worst leaving groups. They are the least reactive. Now, your carboxylic acids and your esters have leaving groups of similar. They fall in the middle. So your carboxylic acid and your esters fall in the middle, but you got your acid chlorides, then you got your carboxylic acid and your esters, and then your amides. That's the order that they go in. So let me say that again. You got your acid chlorides, you got your carboxylic acid and your esters, then your amides. That's how they react. Now, you got addition and substitution nucleophilic. Now, they all have the same first step. You got to have that nucleophilic attack. That's the same. On the electrophilic carbonyl carbon, and it forms that tetrahedral intermediate. Now, the difference between the two is what happens to the intermediate afterwards. Now, aldehydes and ketones cannot undergo substitution because they don't have a good leaving group. That's what happens with them. So aldehydes and ketones, they cannot undergo substitution because they don't have that good leaving group. Now, what about oxidation and reduction? Now, we talked about this a lot in chapter 12, and we did a chapter in this. Now, why do we care about this? And I told you guys when we went over that chapter that this was going to come up later. How do I want to put this? Okay, so with that, carbonyl compounds, they undergo oxidation reduction reaction. They do redox. That's what they do. Now, they can be the reactants or they can be the products. It just depends. That's why I'm saying you can take an alcohol and you can make an aldehyde or a ketone out of it, and it just depends on the degree of that alcohol, and vice versa. So let's get into that. Now, what you see here is you got an alcohol, and if you got oxidation at the top, you got an alcohol that can go to an aldehyde or a ketone, and then it can go to a carboxylic acid. If you're reducing it, it can go from the carboxylic acid to the aldehyde or ketone back down to the alcohol. So it just depends on where it is. Now, these right here, these are the most useful oxidation reduction reaction of the carbonyl starting materials. So you can have the first one, reduction of the aldehydes and ketones to alcohols. Now, aldehydes and ketones, aldehydes reduced to primary alcohols, 1 degree. Ketones reduced to secondary degrees. That's what happened to them. Then you can have reduction of the carboxylic acid and their derivatives. It just depends on what Z is when it comes to those. The identity of Z and then the reducing agent. Now, when it comes to that, you can get aldehydes or those primary alcohols, or 1 degree alcohols. Then the oxidation of aldehydes to carboxylic acids, what happened to that is the oxidation there. So you can just have that. So these are the main 3. And the thing, like I said, I really like about this book and the way that they teach in this book is because they went over oxidation and reduction. And usually we are jumping into aldehydes and ketones. And when I took organic, they really didn't explain oxidation and reduction. They just relied on our past knowledge from General Chem 1 and 2 to apply it to this. But because of this, they made a gap to where they went over a whole chapter on this, which makes sense because you want that to really understand what's going on with aldehydes and ketones and how you can go back and forth with them with redox reactions. Now, when you do this, and we got to look at reagents. So what's going to react with them? And the most helpful reagents that we look at are the metal hydrides. And so there's different ones out there. So you got sodium borohydride, lithium or aluminum hydride. You got different ones that you treat with. Now, when you do those and you follow it with water, you can get an alcohol. So it doesn't matter if you use your metal anhydrides, if you stick with sodium borohydride or lithium aluminum hydride, that's what happens. And you'll get a primary or secondary alcohol. Now, why do we care about those metal hydrides? They reduces the carbonyls. That is what happens. So let's just say if you take the aldehyde and you react it with the sodium borohydride, you would get a primary alcohol. But if you take the ketone and you reduce it with the lithium aluminum hydride with water, you would get a secondary alcohol. And so that's what happens. And then what you have is you end up adding H from your sodium borohydride or your lithium aluminum hydride. And then you got H plus from the water and the addition of the elements of hydrogen gas to carbonyl pi group. That's what happens. Now, you got catalytic hydrogenation of the carbonyls. Now, we back to that again. Hydrogenation of the carbonyls. It reduces the aldehydes and ketones too. And what they do is they use hydrogen in a catalyst to do that. And so when you got compounds that got both carbonyl and carbon-carbon double bonds, you got selective reduction that happens in this case. So with this, you got selective reduction that can happen, and it can be achieved by proper choice of the reagent. And so let's just say you have a carbon-carbon double bond. It reduces faster than when you have a carbon-oxygen group. And so when you have this with a catalyst, it reduces really fast. And so that catalyst really speeds up that reaction. And then you can have carbon oxygen is readily reduced with sodium borohydride and the lithium aluminum hydride, but the carbon-carbon double bond is inert, so nothing will react to it. Now, here what you're seeing is a comparison of the two. So you got 2-cyclohexanol. It contains both carbon double bond and a carbon oxygen. It can be reduced to 3 different compounds depending on the reagent used. So you can have that. Now, here what you see, you got sodium borohydride reductions in the synthesis. So they use it a lot in organic synthesis, and it can go into 3 steps. Now, if you do this in 3 steps, you can get ibuprofen right now. And now, at the moment right now, ibuprofen is really staying on the shelves. Nobody is really touching that. And then, or you can use it here and go in 4 step and you can get muscone, and that's the odor of musk. And musk is isolated from the male musk deer, but it cannot be prepared synthetically in a laboratory in a variety of ways. So they use that a lot in perfumes and cologne. Now, when it comes to these carbonyl groups, we got to get back to stereochemistry. Now, what happens is you got a hydride converts a planar sp2 hybridized carbonyl carbon to tetrahedral sp3 hybridized. Now, here you're going to have an alkyl reagent is used, and when you do that, you're going to get a racemic product. Both of the enantiomers are formed in equal amounts. So what we're doing is this last part of organic, we're really going back to last semester and the earlier part of this semester, talking about enantiomers and stuff. And so this is what happens. And so when you got butane 2-on and then you react it, you get a new stereogenic center and you get SNR. And they are produced in the same amount. Now, why is going to get racemic mixture? Because the carbonyl is planar, and when the carbonyl is planar, the hydride can approach the double bond with equal probability. So it can approach from both sides. Now, it can be selected. That's what we was talking about. It can really be selected. Now, it can be selective of one over the other if you got a chiral reducing agent. So normally a chiral is not going to be selected, but it can be. So CBS reagents, they are ones that can be used to form this selectivity. So these are ones. You got S and R. So what does CBS stand for? Corey, Bosky, and Shibata. And so these chemists form the versatile reagents. And so that's what they named for, because I know y'all probably going like, where did they come up with this? Sometimes the chemists that actually form these reactions get them named after them. And so this is what happens. You got your boron hydrogen bond. It serves as the source of the hydride in the reduction. And then the SCBS reagent delivers the hydrogen negative from the front side of the carbon-oxygen double bond. That generally forms the R alcohol as the major product. Now, if you do the RCBS and it attacks from the backside, it basically does the opposite and forms the S alcohol as the major product. So it just depends on which way it is getting attacked. Now, those ones, they are highly selective. Now, so what can happen is, let's just say you take propylphenol and you react it with the SCBS reagent over water. You're going to get 97% R-based alcohol. You're going to get the R alcohol. And so you're going to get that one. You're going to get most of it is going to be R instead of S. Now, here, what you see is you can see reductions are a key step in the synthesis. And one of those is you got salmeterol, and that's an actin bronchodilator. And so that is what those are mostly used for. So sometimes they are highly selective depending on what drug you're going to use them in. Now, you can also have biological reductions as well. And with this one, when you have those in cells, it always is completely selective and it forms one. Now, in the cells, the reducing agent is NADH. And we are talking about this a little bit in biochem. It's a coenzyme, and it's an organic molecule that can function only in the presence of the enzyme itself. So this is one of them. Now, when you look at this one, Um, this enzyme both binds to the carbonyl substrate and NADH. They keep them in close proximity. And NADH then donates that H minus in the same way as the hydride reducing agent. So this even goes on inside our own body. Now, it's highly selective. So this one is completely anion selective. For example, let's just say you take pyruvic acid with NADH catalyzed by lactate or dehydrogenase affords a single enantiomer with the S configuration. Now, if you do this, NADH reduces in a variety of different carbonyl compounds in biological systems. And it can be R or S, depending on the enzyme used to catalyze the process. So I know Katie and Hannah is probably surprised because they seeing this again, because they just saw this in, I think just for their test that's coming up, this is going to be on there. So NAD plus is a biological oxidizing agent. So NAD plus is basically the oxidized form of this, and is capable of oxidizing alcohols to carbonyl compounds. And then what happens, it forms this in the process, and NAD plus is synthesized to form the vitamin niacin. So this is B3. So this is what it does. It actually is synthesized to form vitamins. That's one of the things we're talking about right now in biochem. Now, are there other agents? Are there other things out there? Well, let's talk about lithium aluminum hydride. It's a strong reducing agent that reacts with all carboxylic acid derivatives. So you got diol H, it got those big bulky isobutyl groups, and that makes it less reactive than the lithium aluminum hydride. Now you got some other ones on there. You got lithium tritert butoxy aluminum hydride. It has 3 electronegative oxygens bonded to the aluminum, and it makes it less nucleophilic than the lithium aluminum hydride. A lot of people just like using lithium aluminum hydride because it's just so simple to use in the way that it reacts. And so with this one, now let's talk about acid chlorides. Now acid chlorides and esters can be reduced to either aldehydes or 1-degree alcohols depending on your reagent. Just depends on what your reagent is. It can be that. All right, now looking at this, okay. When you have the reduction of the acid chloride, it comes off as a leaving group. And we were talking about earlier that when you have this, this is one of the best leaving groups. Now, when it comes to the ester, your CH3O minus come off as a leaving group. Then it's protonated by water to form methyl alcohol or methanol. Now, what happens here? You still have your nucleophilic attack, those pi bonds and reform and that leaving groups depart. And then you got your nucleophilic attack on your H minus, and then it's protonated and then added to that H2. So this is what you see here. Now here, what you see is is Dabal H reduction of an ester to an aldehyde, and then it synthesizes the marine neurotoxin CTX3C. And so that's what that is right there. Now, when it comes to 1-degree alcohols, or those primary alcohols, they are reduced with that lithium aluminum hydride. Now, what it is that it's too strong to stop it at the aldehyde stage, but the milder reagents, they're not strong enough to initiate the reaction in the first place. That's why a lot of people like to use it. That's one of the main reasons. Now, they also use it for the reduction of amides as well. And it forms, the reduction of the amides form the amine groups. And then what happens is, since that NH2 is very poor leaving group, it is never lost during the reduction, and that's for that amine is formed. And this is what you see here. You see a reduction of your amide to the amine, which are lithium with that. So this is what you see here. Now, let's look at these. You can have strong reagents, you can have moderate reagent. Your strong reagent is going to be that lithium aluminum hydride. And this table just basically tells you what starting material and what you're going to get. And so here, mostly for the strong reagent, you're going to get a lot of alcohols, and then you're going to get that amine group. And then your milder reagent, you're going to still get mostly alcohol and those ketones. So when you're doing aldehydes or oxidation of aldehydes, you get different types of oxidizing reagents. All of these you have seen and we have used in the lab, and those are there. Aldehydes can be present in form of other functional groups. You can use silver 1 oxide and aqueous ammonium hydroxide. Aqueous ammonium hydroxide is called Tolling's reagent. Now, ketones have no hydrogen on the carbonyl carbon. They don't undergo this reaction. So mostly just aldehydes. You got other organometallic reagents that can help out. They contain carbon atom bonded to a metal. So lithium, magnesium, magnesium and copper, they're most common ones. Now tin, silicon, aluminum, there are other metals that are found, and these are the general structures that you see. Now, this is the key with them. The more polar your carbon metal bond is, the more reactive your organometallic reagent is. A lot of people like studying these organic organometallic reagents because they can be used in a lot of other things, especially even making different types of polymers. They like to use them as reagents. So you see these around a lot. Lithium and magnesium are very electropositive metals. You got organolithium and organomagnesium contain very large polar groups, and therefore they are very reactive. They are referred to, especially organomagnesium, are called Grignard reagents. Okay, then you got your organocoppers. are called organocuprates. They're less polar and less reactive, but the carbon bears a partial negative charge if you look at the organometallic reagents. I've used these a lot, Grignard reagents. I've used them a lot. Not so much the copper, but the Grignard reagents are used a lot by organic chemists. Now, how do you prepare these compounds? You react them with an alkyl halide and the corresponding metal. With lithium, the halogen metal exchange form organolithium. With magnesium, the metals insert into the carbon hydrogen bond. That's what forms the Grignard reagent. And I remember when taking organic chemistry, we had to make our own Grignard reagents. So usually we did that in lab and made our own Grignard reagents. All right. Now, with solvent, we can also stabilize the Grignard reagents. They are usually prepared in diether ether, and although you have two oxygen atoms complex with the magnesium atom, so usually the stabilizing the reagent, you have a Lewis base and a Lewis acid interaction. So even when making these, you have that Lewis base and your Lewis acid interaction. You can have organocuprate compounds. You can use metallic salts with that. And so usually you have the copper salts, and that's how you form these. And here you have lithium dimethyl-cuprate, and that's what can form there. Let's see, where are we right now? Okay, I think I'm gonna probably go a little further. So you got acetylide ions. They form also organometallic reagents. Now, these ones that form, they are pretty much organosodium. Sodium is even more electropositive, so that carbon sodium bond is the best described as ionic rather than polar covalent. So because of that, that's what they are looking at. All right, so you can have acid-base reactions of those organometallics. They are strong bases. They readily get rid of those protons from water to form those hydrocarbons. And you can have those other reactions when you have your hydronium ions. So the OH protons are the alcohol, your carboxylic acids, and then your NH protons of the amines. So you can have those that actually react as well. Now, why do we use them? We use them, especially our Grignard reagents. They prepare from alkyl halides. You can take them and convert the alkyl halide into an alkane. Now, the organometallic are also strong nucleophiles. You can find ways to make new carbon-carbon bonds. Why do we care about these organometallic compounds? Like I said, they can form a variety of things. Like I said, I have used them in different type of organic synthesis when it came to polymers. A lot of them are using in making products from the gasoline industry. Crude oil, it can be used in all of that type of stuff. What about this? Now, one of the things we look at is you can do functional group transformations. What do they mean? Basically, you can react them with aldehydes and ketones to get alcohols. So you can also use those organometallic compounds and react them with the carboxylic acids and the derivatives, and you can get ketones and you can get a 3-degree alcohol. So you can do those as well. And like I was telling you, give me 1 second. Now, what happens is you can react those organic metallo compounds with other functional groups as well and still get your carboxylic acid and get an alcohol. So that's what it's showing here. Now, can you add them to the aldehydes and ketone? Now, if you added the organolithium or the Grignard reagent followed by water, you can still get those alcohols, and you can get primary, secondary, so 1 degree, 2 degree, 3-degree alcohols. You can still get those. What I'm going to do, you guys, I am going to stop right here for today. We'll finish up the rest of 17 and go into 18 on Wednesday. I am going to try to see, can I sit down and put together your, and I know some of you guys need it for both classes, but I am making a note that this week that I am going to put in your rubrics for your paper and your presentation. And so I'm going to sit down and do that. Videos, let your classmates know, the ones that couldn't meet today, let them know that the videos will be uploaded to Dr. Wanda Jones' YouTube page. Like I said, the internet being a little better and more stable, they should upload a lot faster now. So I'm going to do that. If you got any other questions, you guys make sure to email me. And like I said, I'll be checking my emails and everything. So make sure you send me an email. And I will talk with you guys on Wednesday. So this is all for now. We'll pick this back up on Wednesday. I think that's enough for today. So we'll pick this back up on Wednesday, you guys. If you got any questions, like I said, let me know. And I will talk to you guys later. All right? Have a good one.